Hello and welcome. In this video I will be showing you a model of a flat Earth, and I wanted to show you how the model doesn't match the data that we have available on the internet. The data I'm using for this model are from SunCalc and from timeanddate.com, and the purpose here is to show you that either the flat Earth model is wrong or the data from those sites are wrong. And I want to focus on sunlight hours and angles of sunrise and sunset for this video. So I'll just start by explaining how I made this model and what this shows you. This is the flat Earth as seen from above. In the center here, the red dot is the North Pole, and I made a little white circle to sort of make that easier to visualize. Then you have the equator here, and the equator is just the halfway point from the North Pole to the outer rim. On the outer rim of this circle is where Antarctica would be. On the flat Earth model, in case you don't know, the Antarctic is sort of a huge ice wall. There are different theories about how this works, but this is generally the plan that all flat earthers will agree on. What's not included here is sort of the dome above the flat Earth, where the stars and probably the sun and moon are for most flat earthers as well. But yeah, this is just a basic, simple model. The numbers I used for this, or the distance from the equator, from the North Pole to the equator and to the outer rim, are based loosely off of an animation made by a YouTuber called Steve. He has a really nice animation of how he thinks the flat Earth map works. So he's really talented in animating. The problem is that I don't think his model works at all, and I really hope he could have focused his energies on something more productive. But oh well, he makes a really good animation anyway. The two circles here are the tropics of. This is the Tropic of Capricorn, and this is the Tropic of Cancer. In case you don't know, if you live along this circle here, the Tropic of Capricorn, once a year on December solstice, the sun will be right above you at noon. And the same goes for the equator. During equinox, that is in September and in March, the sun will be right above your head at noon. And for the Tropic of Cancer, the same will be the case for June solstice. The way I made these lines is actually I just used the data provided by Wikipedia. They say pretty much an estimate of where those lines are right now, and then I just calculated them from out of the equator. So this model will not be 100% accurate. I just gotta get that out of the way. It's a demonstration of how it works, but for the purposes of what I'm doing, it doesn't really matter that it's not 100% accurate. It will be accurate enough to show why it fails. These lines here are mostly for visual aid, but there are 24 of them, 15 degrees of difference of angle between each of them. This line here represents the Greenwich line going through Greenwich in Great Britain. And so if you have the sun here in June, for example, each line the sun crosses is 1 hour, because obviously it uses 24 hours to make a full circle. And so I can use this to sort of roughly estimate the time the sun uses to cross a certain distance. You'll also notice I have 3 suns here, and those suns are placed right above these lines, as you can see. These circles are the amount of sunlight that the suns produce on the flat Earth model. And this you might not know this, but this is how the flat Earth model explains day and night. If the sun was actually a ball which spread lights in all directions, like on the globe model, then you would kind of expect the whole disk to be lit up. On the flat Earth model, it acts more like a spotlight. Either that, or you got things in the air making it so that you can't see light from that far away. There are different explanations for this, but basically this is sort of the general idea. The sun only lights up a circle around it. I made these circles using, again, data from the internet. This is the farthest south you can have 24 hours of sunlight during summer. And the same thing for the December. This is the place farthest north where there is no sunlight in winter. And the reason I did that instead of going for where there was 24 hours of sunlight here is that the flat earthers will not accept that there is midnight sun in the southern hemisphere. So there's that. The equinox circle is really just an average between those two. Again, it's not perfect, but it's good enough. I also plotted out some cities. I can actually use this model to plot different coordinates on this map pretty easily using coordinates and this angle tool. These 14 cities here are placed 10 degrees of latitude apart. So you got Longyearbyen at 78 degrees, representing the 80 degree mark. It's just that there is no city at 80 degrees north. That would be 80 degrees north from the equator, in case you don't know. Then there's Tuktoyaktuk here at 70 degrees, Oslo at 60, Frankfurt at 50, and so on. Pontianak is on the equator, so it's 0 degrees. And this here is in South America, and this is the farthest south you get, Rio Gallegos at 50 degrees south of the equator. If you want to be a little bit imaginative, you can see here that this is Europe, with Oslo in Norway. Great Britain would be about here. Sorry, this is the Greenwich line, so I guess it would be here. Egypt is here, so this is sort of Africa. Port Louis, I'm not really sure where it is, but it's probably east coast of Africa somewhere. This here is in Indonesia, Pontianak. Cebu City is in the Philippines. Aomori is in Japan, so this is Eurasia. Here's Hawaii. Tuktoyaktuk is in Canada. And Aracaju, something, is in Brazil. And South America sort of stretches along here. So you can see the continents do get a bit wonky sometimes, but yeah. So what I can do with this is I can simulate sunrise and sunset using these suns here. So in Hilo, for example, in Hawaii, I can match the line here with the point, and this is sunrise. As the sun moves along, I can count the hours until sunset. So if we do that, for example, for Port Louis here, we get, so this is in the middle between these ones, so 1, 2, 3, 4, 5, 6, 7, 7.5 hours or something. Yeah. I can also calculate it more accurately using this angle tool again, because 360 degrees, I can convert that pretty easily into minutes and even seconds if I want to. And I have done that. So we're going to look at the data that I've collected. Let's see. This here is a list of the data that I've collected for the cities. You can see in the upper left, you got the city column with all the cities, and they are sorted according to how far north they are on the map. You can see the degrees there in case you want to know. Longyearbyen 78 degrees, Pontianak 0 degrees equator, and below that 10, 20, 30, 40, 50. They're actually supposed to be negative degrees, so south of the equator. I got 3 sets of columns following that for summer, which would be summer solstice, equinox, which I've only used March equinox for this, and winter would be winter solstice or December solstice. And you can see that the times I've used are all UTC times, so they're all sort of they're following the same Greenwich line clock, just for convenience sakes. But what I can do with this is I can calculate the total amount of sunlight. And this data is all from suncalc.com and from timeanddate.com. So if you look at the total amount of sunlight in summer, for example, for Longyearbyen and Tuktoyaktuk, there's 24 hours of sunlight. So it's midnight sun. Oslo has 18 hours and 51 minutes of sunlight. Frankfurt has 16 hours and 23 minutes, and so on, until you get to Rio Gallegos, which only has 8.5 hours of sunlight during our summer here in the Northern Hemisphere. For the equinox it's pretty much all of the cities have about 12 hours of sunlight, between 12 and 13 hours of sunlight. So it's very equal there. And in winter, you can see that the tables have turned, and so you have Longyearbyen and Tuktoyaktuk with 0 hours of sunlight. Oslo has only 6 hours, and Rio Gallegos has 16 hours and 40 minutes. And if you compare that to Frankfurt am Main in summer, you can see that they got 16 hours 23 minutes. Rio Gallegos has 16 hours and 40 minutes, so it's pretty close. It's pretty much flipped. What I've also done in the bottom here is I got 3 columns again, summer, equinox, and winter. And on the left hand, you got the model, which is calculated using the model I made in GeoGebra. I don't know how to pronounce that. And on the right hand, you got the column showing the difference between the model and the data. And you can see already from Oslo, and it's pretty consistently, the farther north you get on the flat Earth map on a model, it gets more accurate, because the whole flat Earth map is sort of based on the northern hemisphere, and then the southern hemisphere gets really distorted because a circle or a flat disk will get much more surface area as it gets towards the edges, while the globe Earth will curve back towards Antarctica. And so the further south you get, the worse the difference gets. And you can see during summer it's not too bad. Maybe Oslo has about 1 hour less sunlight than the data shows, and I live in Oslo, so for me that would be during summer right now I would have 1 hour less sunlight than what the data shows me. And so I can test this pretty easily just by waking up early in the morning, watching the sunrise, and waiting until evening and watching the sunset. And if there's 1 hour of discrepancy between my model and between the data, or if the data matches my observations, then the data is correct. But as you get further south, the discrepancy gets bigger. And in Pontianak, the equator city, you can see there's 3 hours of difference. And in Rio Gallegos, 50 degrees south of the equator, you have 4.5 hours of difference. And this again gets worse during equinox. Oslo now has 1.5 hours difference between the model and the data. Pontianak on the equator again has about 4 hours of difference. There's 4 hours less sunlight in Pontianak than what the data shows, and Rio Gallegos has 7 hours difference. And during winter, it gets worse again. If you look at Pontianak now, according to the model, they should be getting 6 hours and 44 minutes of sunlight. according to the data, they should be getting 11 hours and 45 minutes. 12 hours, pretty much, of sunlight, which means there's a difference of 5 hours and 23 minutes. If you look at Rio Gallegos, you can see how extreme this can get. The model predicts 5 hours and 13 minutes of sunlight. In reality, they have 16 hours and 40 minutes of sunlight. So this model steals 11.5 hours away from Rio Gallegos. And this makes sense because the flat Earth, the data that I have is based off of a spherical Earth. And on a spherical Earth, you would have 24 hours of sunlight at some point in the south as well as the north. So you'd have Antarctica with 24 hours of sunlight, while on my model you can see that during December equinox this circle is only tracing a small segment of this circle here. So it has to move around 24 hours to light up the whole thing. And so this discrepancy makes a lot of sense. Now what this means is that all the data on timeanddate.com and all the data on suncalc.com and all the data provided to us about sunrise, sunset, and sunlight hours must be wrong, or this model is wrong. And the problem with that conflict there is that you can very, very easily test for yourself how many hours of sunlight you have on any given date. If you live in Australia or in South Africa or in South America here, you can go out early in the morning, watch the sunrise. You can go out late in the evening, watch the sun set, and you can count the hours in between. And if it doesn't match up with the data given to us by, NASA and other organizations, then that data is wrong and something is wrong. If it does match, and I can pretty much guarantee you that it will match or someone would have noticed, then this model is wrong. The only way you can make this work is if you make this circle here not a circle but some sort of, during equinox you would have some sort of semicircle. And I don't really know how you would manage to sell that idea. The second thing I wanted to talk about is also about the sun, but this time it's about the angles of sunrise and the angles of sunset. Both suncalc.com or net or whatever and timeanddate.com shows you not only the hours of sunrise and sunset and all that, they also show you the angles. What that means is that if you're standing in, I'm standing in Oslo, if I'm looking directly north to true north here, not magnetic north, I can use the data provided to me by the internet, measure an angle going pretty much, so and so many degrees. Let's see, like this. I can measure so and so many degrees, and this is where sunlight will come, and I've plotted that for some cities. So Aomori, for example, in Japan, has sunrise in June is in this angle here, and that means if I'm standing in Aomori looking directly north and turning my head 57 degrees to the east, or clockwise, this is where the sun will rise according to the data. And same goes for sunset, same goes for March and December. All you really need is to know the angle, and you can calculate it if you're facing north. And if the flat Earth model is true, then this data should be pretty consistent with with what I can get here. So I've done this on 3 different places: Aomori in Japan, Pontianak on Equator in Indonesia, and Rio Gallegos. Again, I'll just turn the other cities off. So we got this the June solstice sun here, and this is sunrise when this line crosses the point. And we can see, if we draw a line between these, you can see that the angle is off. The June solstice sun on the flat Earth does not rise where the data predicts that it will. And we can even calculate the difference. Let's see, if we turn on cities here, the difference is 10 degrees. So it's not a huge difference. It might even be consistent just because my model is not completely accurate. However, as you get to equinox, the difference will grow. Sorry about this. So we went from 10 degrees to 15 degrees. And if we do the same for December, let's have sunrise here. We can measure this angle, and the difference is about 16 degrees. Now you might probably predict that the difference is going to be greater for Pontianak. And Pontianak is an interesting example of why this will never work, actually. Because as you can see here, during March equinox, the sun will rise pretty much exactly in the east and set pretty much exactly in the west. And this will be true all over the equator. Let me just show you here. This is the sun, and it's not rising in the east, it's rising in the northeast. So in order for this to work, the sun would have to appear somewhere on this line here. So let's say the sun is over here, right? Now it's consistent. It's in Pontianak, the sunrise is in the east, but it's not going to be in the east for other cities along here. It's going to be slightly off. And if we look at all these cities here, it's not matching up at all. Now let's just continue looking at the degrees here. Pontianak, this is sunrise. For June, we get a difference of 7 degrees. Let's see. Sorry, that was the wrong sun. For June, you get a difference of 23 degrees. For equinox, you get a difference of, let's see, 30 degrees, pretty much spot on. And for December, let's see, sunrise is here. You get a difference of 34 degrees. And let's do the same thing for Rio Gallegos. Let's see, sunrise is here and here and here. So again, during March, the sun should be rising pretty much exactly in the east and setting pretty much exactly in the west, but the angle is completely off. Let's see, for June, it's 32 degrees off. For March, it is 52 degrees off. And for December, it's 77.53 degrees off. The sun is supposed to rise in the southeast, and instead it rises in the northeast. It's pretty ludicrous. And imagine, if you will, the December solstice along this 50 degrees south line. On every point, this sun is supposed to be rising in the southeast. So for that to work, you would have to have the sun somewhere here along this circle, outside of the globe, or sorry, the flat disk. And this data is never going to be consistent with the flat Earth model. So again, you can see from both of these examples that the flat Earth map does not match the data given to us by NASA and other organizations. It does not match the data that you can easily go out and see with your own eyes. It does not match at all. And so either the data is completely wrong, every single data is completely wrong, all the data that you've gathered yourself as an amateur astronomer is also wrong. Something must be wrong with your eyes or something. Or this model is not accurate. And I can't really think of anything that will make these angles match up with all the points of the Earth. There's no way you're going to get that, as far as I can think at least. If you got any solutions for this on a flat Earth model, which is consistent with all the things that flat earthers say, then please share it with me, and maybe I'll rethink my position. But as of now, I can't really see this model ever working out with the data that we have. So again, this goes into the whole idea that if you believe this is the Earth, then it should be consistent with itself. And I don't think it is. And so this is not a proof that the Earth isn't flat, but it is pretty strong evidence that it really isn't. Or at least that the sun is not circling 3,000 miles above the surface of the Earth. Well, I don't know. Maybe I proved this to someone. Maybe I convinced someone. I probably didn't, but I hope some of you will watch this and enjoy it. And if you want to make these things yourself, it's pretty easy. So thank you very much. Bye bye.